Now that we know how to write HO and HA, let's now go to the part, how do we know whether we reject or we not or we fail to reject the null hypothesis? Now, let's remember an important principle in hypothesis testing. Say, for example, the null hypothesis is that the population mean is equal to 7. Then the alternative hypothesis is that the mean is not equal to 7. Say we get a sample size of 25. Sample size of 25. There you go. Sample size of 25. Sample mean of 8.6. Just because 8.6 is not equal to 7 does not mean we reject already. Because that 1.6 difference, the difference of 1.6 might not be significant. It might not be that important depending on the situation, the context, and the probability. Because maybe that one sample size of 25 is just the one that got 8.6. If you get other sample sizes of 25, it might not be 8.6. It might be closer to 7. It might also be equal to 7. So we don't simply reject just because they're not equal. So, because like what I mentioned, it might not be large enough, not small enough, or not different enough from the value, statistically speaking. So we don't just simply do that. We have to do and we have to determine important values and do 3 other steps. So we define first some values that we need to be familiar with. First is alpha, which is the level of significance. This is the probability of rejecting HO when HO is true. And this is one of the bases that we use when we are going to do a hypothesis test. This is also the leverage or the probability we're allowing ourselves to make a mistake, because it's a mistake, it's wrong, when you reject a true HO. And since the sample is not the entire population, we have to allow ourselves to make that mistake. Now, the critical value, the next term, that is the value of the test statistic that serves as the boundary between the non-rejection region and the rejection region for the null hypothesis, which later on we can actually show when we do our hypothesis test. Because it's the critical value that we use as basis to whether reject or we have failed to reject. The test statistic is the quantity used in deciding, because that's what we compute. Now, once we go into computer softwares, although the critical value can also be used there, the more widely commonly used to determine whether the hypothesis is rejected or not is the p-value. Using the p-value. It's the probability of a particular sample statistic or a more extreme statistic occurring if the null hypothesis is true. There you go. Now, the critical value and the p-values you might have seen in this slide. The critical value approach and then later on the p-value approach, those are the two approaches which is not that different when we do a formal hypothesis test. So, step 1, we state our HO and HA, and that's what we already did, we practiced in the previous video. Then we compute the value of the test statistic. Then we determine the critical value from a table, whether a Z table or a T table, or there might be other tables to use. Then we compare using a decision rule. In the p-value method, after computing the test statistics, so steps 1 and 2 are the same, whether you are in the critical value, or the p-value. Steps 3 and 4 will be different. For step 3 in the p-value approach, you also compute the p-value. In step 4, you use the p-value and compare it with alpha, or the level of significance. And that's when you state your conclusion. Now, for alpha, it's usually 0.10, 0.05, and 0.01. Although it would be in between 0 exclusive to point 10, inclusive. Now, this is the general rejection rule for the critical value approach, which is important, which direction is important. Because if the direction is a lower tail test, then this is the rejection rule. If it's upper tail, it's a different rejection rule. If it's two tail, it's either or of the two. If it's lower tail, then we reject HO if the test statistic is less than the critical value. If it's upper tail, we reject HO if the test statistic is greater than or equal to the critical value. For a two-tail test, it's either one of the two. So this is an example of our specific rejection rules when we go to our specific hypothesis tests. For the p-value approach, it's just one. Reject HO if p-value is less than or equal to the level of significance. Why is that? The p-value is the probability that the sample statistic you computed will happen if HO, let's go back to the definition. There you go. If the null hypothesis is true, then p-value is the probability of the particular sample statistic that you computed happening. So, let's go back here. If the probability of the sample statistic of the test statistic that you computed is smaller than the probability that you making the mistake of rejecting a true HO, might as well reject HO because the probability that your test statistic will happen if HO is true is smaller compared to the probability that HO is rejected. So might as well reject HO because this has a smaller chance of happening compared to this. And more or less, this is the interpretation for this one. Although it depends on the level of significance given in the problem. But whether or not it's HO or HA, remember that conclusions are not always correct because we only got sample information. So that's why we have to take note of type 1 and type 2 errors. Of course, when the null hypothesis is true and we do not reject it, it's a correct decision. However, if the null hypothesis is true and we reject it, then we are making what we call a type 1 error. And type 1 error, the probability of making of that is alpha. And that is set by the problem because that's what we use for our decision rules. Now, if we reject a false HO, then the probability of that is called the statistical power of the test. But if we do not reject a false HO, that is what we call now a type 2 error. And the probability of that is beta. So again, if we reject a true HO, that's a type 1 error, and the probability of making of that is alpha. The probability, not rejecting a false HO is a type 2 error, and the probability of that is beta. And the complement of that is the power of the statistical test. And those are the basic principles of statistical hypothesis testing.